Okay, so I'm going to say a few more things about conformal field theory, and then I'm going to take a break and talk about lattice gauge theory, lattice field theory and lattice gauge theory for a while.
Sure.
And then I may come back to conformal field theory. I think that the book, this big yellow book, the one that's called Conformal Field Theory, which you can get, by the way, you can get the whole PDF file from b-ok.org.
Okay.
You guys know about that, right?
Yeah, you mentioned this website to us, I think, at the beginning of last semester.
Yeah, I'm a little naive. I didn't realize that it's not 100% on the up and up.
B-OK.
Well,
So I logged into it on my Sandia computer.
you can't log into it from Sandia.
I'm not supposed to.
Oh, no. Is that a hyphen or an underscore?
That's a
It's a
hyphen,
hyphen, okay.
not an underscore.
Sure.
Raise it a little bit. b-ok.org. I think it's enormously useful because there are a lot of good books and there's not a lot of money, at least in the hands of students and, for that matter, the hands of professors. And so if you're not on Wall Street, you need something like b-ok.org.
Is physical mathematics on it?
Huh?
Is physical mathematics on it?
It was on it, and Cambridge took the link down.
Ah.
So that's the reason why it hasn't yet been attacked by various organizations legally. It's that if you want us to take a link down, we'll take a link down. That's their attitude. So I'm going to say first a couple of things about that are sort of related to some of your questions last time, but they don't form a complete answer to them. It's just I just want to do the finite transformations for the case of 2D Euclidean space. And the idea is to get back to the definition of a conformal transformation in flat space. And it's that we start out with a metric eta ik, which is either the identity in Euclidean space or it has one or more minus signs in pseudo-Euclidean space. There's a dilation factor, and then that's the new metric. On the other hand, metrics transform this way. Partial xj, partial x prime I, partial xl, partial x prime k, gjl. And the inverse metric, of course, transforms the other way. Eta prime ik is partial x prime I, partial xj, partial x prime k, partial xl, eta jl. And for a general, whoops, I put a G in there by mistake because in fact, you could replace these by G's and they would be the standard transformation. In fact, I might as well do that since these are this is just a more general way of writing those things. So, if you then realize that in 2D Euclidean space, the metric is just that, then what you have is that omega, the scale factor, and is the same thing as eta 0, 0 times omega. And so this equation, setting I and k equal to 0, we get this equation. take this equation, set I and k equal to 0. I'm sorry, take this equation, set I and k equal to 0 and g equal to eta, and what you get is that this is partial x prime 0, partial x 0, partial x prime 0, partial x 0, eta 0, 0, plus partial x prime 0, partial x 1, partial x prime 0, partial x 1, eta 1, 1, and this is the same thing, of course, as partial x 0 prime partial x 0 squared plus partial x prime 0 partial x 1 squared. So that's one equation, that omega is that. Now you set eta, I and k equal to 1, and you get the equation omega is omega eta 1, 1, 1, and this gives you partial x prime 1, partial x 0, partial x prime 1, partial x 0, eta 0, 0, plus, I realize that this looks very simple, but I think it's actually useful occasionally to see something expanded this way, because in general relativity, you normally write things in with the Einstein summation convention, and you can lose track of what that actually means. So what we have here is partial x prime 1, partial x 1, partial x prime 1, partial x 1, eta 1, 1, and this thing is the same as partial x prime 1, partial x 0 squared plus partial x prime 1, partial x 1 squared. And then if you take this same equation and set I equal to 0 and k equal to 1, what you get is 0 is omega eta 0, 1 is equal to partial x prime 0, partial x 0, partial x prime 1, partial x 0, eta 0, 0, plus partial x prime 0, partial x 1, partial x prime 1, partial x 1. And this one, unfortunately, times eta 1, 1. And this doesn't collapse very much. This just gives us partial x prime 0, partial x 0, partial x prime 1, partial x 0 plus partial x prime 0, partial x prime 1, partial x 1. If you do the 1, 0 instead of 0, 1, you don't get anything new. These equations are equivalent to partial x prime 0, partial x 0 squared plus partial x prime 0, partial x 1 squared is equal to partial x prime 1, partial x 0 squared plus partial x prime 1, partial x 1 squared, and one other equation, which is partial x prime 0, partial x 0, partial x prime 1, partial x 0 is equal to, now we get a minus sign, partial x prime 0, partial x 1, partial x prime 1, partial x 1. Okay, well, we can can satisfy these equations by setting partial x prime 1, partial x 0 equal to partial x prime 0, partial x 1, and partial x prime 0, partial x 0 equal to minus partial x prime 1, partial x 1. So, I guess let's look at the second equation first. If we use the top equation, right, if we use the top equation, we replace this first derivative with the second derivative without the minus sign, then we replace the second derivative with, I'm sorry, I've got this backwards. Yeah, we use the second equation first. This one turns into that one with the minus sign, and this one turns into that one, which is this one, without the minus sign. So you satisfy the second equation. And similarly, you satisfy the other equations. Basically, what this is saying is you can go from 1, 0 to 0, 1, and 0, 0 to 1, 1. And in as much as here we're squaring everything, here we go from 0, 0 to 1, 0, and here we go from 0, 1 to 1, 1. So you see you can satisfy them by these equations. And on the other hand, these equations, or the Cauchy-Riemann equations, which say that a function f of z equal to x prime 0 plus I x prime 1 is an analytic function of f of x0 plus I x1. And on the other hand, you can also satisfy these same equations with slightly different equations, namely, instead of these, you can have partial x prime 1, partial x0 equal to minus partial x prime 0, partial x1, and partial x prime 0, partial x0 equal to partial x prime 1, partial x1. And these are the equations for an anti-analytic function. And so this is for the case of f of z bar equal to x prime 0 plus I x prime 1, where this is f then of x0 minus I x1. And so the anti-analytic Cauchy-Riemann equations, so the anti-analytic CR equations are u sub x equals minus v sub y, and v sub x equals u sub y. So these are the opposite of the Cauchy-Riemann. The Cauchy-Riemann are u sub x equals vy and v sub x equals minus uy. And I'm using subscripts and to indicate differentiation without the comma.
Okay, yeah. So the first equation that you wrote was indeed these anti...
When you say first equation,
sorry,
equations.
This guy on the left. You have
This?
down one, and then to the left side of that, or... Yeah, those are the anti-Cauchy-Riemann equations, right? I suppose so, yeah.
All right, maybe I
But
screwed
this-
up my
this
notes, but
anti-analytic
these are supposed to
way,
be the
right?
Cauchy-Riemann equation.
They're the Cauchy-Riemann equations for an anti-analytic function, right? And on the
Really?
right-hand side, is that true? Isn't that true?
All right, let me get my pen. Is that? I thought I had done it.
I feel like the bet, right? Because if you want ux to be equal to vy, well, the second equation says ux equals minus vy. So
The x
x
zero.
prime 1 is...
X0 is u.
All right, let's-
yeah.
All right,
X, yeah,
let's
x
just
zero
translate this to see. This thing says v, because x1 is v, this is vx equals u y. That's the Cauchy-Riemann. Oh, you're
That's the
right.
anti-analytic
Damn
function.
it. Okay, so, well, that's great that you found that you are starting once again your candy store for the day. So let's just say then that this one would be, okay, so what we need for the ordinary Cauchy-Riemann is this with a plus sign. And anyway, the upshot is that you can solve these with you can have the finite, for the finite transformations, x0 and x1 prime have to be analytic or anti-analytic functions of of x0 and x1. Shall I say something about why angles are preserved with an analytic function? Remind you guys of that?
It's been a while.
All right, let me remind you then. If you have an analytic function, then we have dz is what? It's going to be f prime, or rather df, is the derivative f prime dz. And if we use a slightly different, and in other words, if we have dz going this way and dz prime going that way, then over here we're going to have df and df prime, and the relation is df prime, well maybe I should write this as df dz. Now, the whole point of analyticity is that the change, that the derivative in the dz direction and the derivative in the dz prime direction are the same. Okay, that's the whole idea of analyticity. That you can take the limit of the change in the function divided by the change in z. You can take dz to 0 from any direction, and that's the definition of analyticity. And since these things are equal, then the angle comes out from this, that this is df prime over df, and that would be epsilon e to the I theta prime over epsilon e to the I theta, where these are just the dz's because this term cancels. And so this is e to the I theta prime minus theta. And so this is the angle that you get in the image plane, and it's the same as the angle in the ordinary plane. There is one exception, or not one, but there are actually many exceptions if the derivative should vanish. If the derivative vanishes, then you see df is a half df dz squared, dz squared. And so then the angles double. That is to say, d phi is then 2d theta. If the first derivative vanishes but not the second. And in general, df prime over df is going to, which you can write as e to the I phi prime over e to the I phi. This is the nth derivative dz to the n over the nth derivative dz to the n, and this is then e to the n I theta prime minus theta. So that's the change. One subtlety there. There's a function called the Möbius function. And it is f of z equal to az plus b over cz plus d. And the Möbius function just says that the determinant shouldn't be 0. So AD is not equal to BC. And when AD is equal to BC, this is just a constant. So I guess this can be the general Möbius function. But if AD is BC, then it's just a constant function. Anyway, so these are finite, finite conformal transformations. In Euclidean 2 space, you have the new coordinates x0 prime, x1 prime are analytic or anti-analytic functions of the old coordinates x0 and x1. However, you see, in general, an analytic function might look like this: p of z over q of z. And if this has multiples, if the numerator has multiple zeros, and indeed, if you have an entire function, you'll have multiple zeros. But if you have multiple zeros, the thing isn't invertible, because there are many z's that give f equal to 0. So you can't invert it. So if you want the thing to be invertible, then you can only have 1 0 in the numerator. And the people who are serious about conformal field theory like to think about mapping the whole plane into what's called the Riemann sphere. And the way you do that is you take an arbitrary point and you draw a line to the North Pole. Wherever that hits the unit sphere, that's the point. And
however, I have a question. This Möbius function is not, it seems not to be analytic though.
Say that again?
It seems to not be analytic, the
What?
Möbius function.
The Möbius function?
Yeah.
Well, it's analytic. It means it has a pole.
Okay. So it's, oh, wait. Okay. Yeah, okay, sorry, I'm confusing analytic with entire. I guess it's not entire. It's not analytic in the entire
All right,
context.
look,
it's
to
meromorphic.
tell you the truth, these damn names and definitions I keep. You're attached to the internet, right?
To some extent.
So
What are you looking for?
why don't we look up,
I think I'm
let's
confusing
look
with
up
entire.
analytic, and I think analytic functions can have poles.
Yeah. It's probably true.
And look up holomorphic also. I think holomorphic means exactly the same as analytic.
I think holomorphic means no. No poles? Because there's also this concept of meromorphic, right?
Meromorphic means that it's analytic but has some poles.
Yeah. So that's,
Meromorphic means analytic everywhere but does have some poles.
yeah. So this seems like meromorphic. And it is
Right.
analytic. It's just I was confused.
It's analytic and meromorphic.
Holomorphic.
So it's a meromorphic analytic
Yeah,
function.
yeah,
Okay.
yeah. That
And
makes
holomorphic
sense.
means,
I think holomorphic is that you have no poles, right?
homomorphic is the same as entire then.
Yeah, I guess.
All right, let's check that out, whether holomorphic means entire or not.
Let's see. Real versus complex.
In any event, let me just, while you guys are doing that, what people do in complex variable theory often is they take the point of it, they replace the complex plane with the Riemann sphere, which is just a unit sphere in which the point, the north pole is quote, the point at infinity.
Yeah.
And of course, it's not one point at infinity, but as this point here goes to infinity in the complex plane, this thing goes higher and higher and eventually approaches the North Pole.
Yeah. Okay. So here's the thing: holomorphic is analytic everywhere in its domain. So the idea is you can always restrict the domain of a function such that it is holomorphic, right?
All right.
Yeah. But the idea is entire means that the domain is actually the entirety of the complex plane.
Right.
Yeah.
Okay.
Yeah, yeah. So that's
So holomorphic and analytic are the same, no?
holomorphic and analytic. Yeah. I mean, essentially. I mean, I guess analytic is more so a property of a function at a point, and holomorphic
Yes.
means that at every point in its domain, it's analytic.
Okay.
Entire means that its domain is the entirety of the complex plane.
Yeah. All right. Anyway, people like to have the function be meromorphic and that it maps the Riemann sphere onto itself in a one-to-one way, and for that reason you can't have more than one pole in the denominator, because the denominators, that would, in other words, the point of infinity is the zero of the inverse function, I guess. All right. Anyway, this is what you have if you want. This is called the special conformal group. And what's interesting about this is that this is the same, these transformations are, or these matrices, A, B, C, D, these are 2 by 2 complex matrices. 2 by 2 complex matrices of determinant 1, because one restricts AD minus BC equal to 1. And once you do that, what you have is what's called the special linear group, SL2C, on the complex numbers. A, B, C, and D are in general complex. And this thing is isomorphic to SO31. And in fact, this is the group that acts on the two spinners. If you talk about left-handed and right-handed spinners, in other words, you write a Dirac field, which is 4 components, as a 2-component left-handed field and 2-component right-handed field. This thing has 2 inequivalent 2 by 2 representations, and one acts on L and the other acts on R. And okay, all right, I think I've said enough there. Okay, now we saw last time that for infinitesimal, for the Minkowski 2 space, for infinitesimal transformations, we could go to light coordinates, everything was fine. I was trying to do that this afternoon for finite transformations and ran out of time. All right, let me switch now to something that is kind of related to conformal field theory, because one of the applications of conformal field theory is critical phenomena and phase transitions and so forth. And one way to study such things is on a lattice. And so basically, last semester we rushed through the path integral business. So if you want to hear anything more about the path integral, let me know, because I'm going to sort of use some of it now. The partition function, is at inverse temperature beta, 1 over kT, is the trace of e to the minus beta h. And, a trace of e to the, yeah, all right, this is the partition function for the case of maximum entropy. So this is the Boltzmann distribution. And that's the trace of e to the minus beta h. More generally, z of beta. Well, actually, it isn't simply z of beta, because if you are more general. All right, let me just say what is more general. Namely, the mean value of some operator A at some temperature. I guess we don't have temperature if we don't have the maximum entry situation. So let me just say what the mean value of that would be. This would be an integral e to the minus the Euclidean action, and if this is let us say, a scale of field theory, then you are integrating actually, now that I think about it, this is at a given beta, and the beta is related to what the length of the time integral, or the imaginary time integral, is in that exponential. And so this is the trace of e minus beta h times the operator A, and this is h is a function of phi, and so is A. So that's a ratio of two path integrals, and the path integrals are Euclidean space path integrals. So the question is, how do you approximate these? And one way to approximate such things is to, well, of course, let me just mention, if this happens to be quadratic, you can just do the integral. You can do both path integrals. Well, it depends on what A is, but if A isn't too complicated, you can do the path integral. So the question is, what do you do to approximate this on a lattice? And what you basically do is you divide space-time into a space-time lattice, and if you're in Euclidean space, then the direction in the t direction corresponds to inverse temperature. And so for example, as at low temperature, beta is very high. Beta very high means that the t integral here goes a long way. in principle, your lattice in the spatial direction should go to infinity, and the lattice in the time direction should go a long way if you're at temperature 0, a short distance if you're at high temperature. And these configurations are actually all loops in time. That is to say, you go from a function phi of x vector to another function phi of x vector, the same function phi of x vector, at the final time. So this is imaginary time 0, and this is imaginary time beta.
Wait, so you were saying that the imaginary time beta is the vertical direction in your lattice? So why are we not just like imposing periodic boundary conditions on the lattice? That's exactly
periodic.
we put it on a cylinder?
That's right. We're periodic in the time direction. What you do, periodic in the time direction is necessary mathematically. Periodic in the space direction is a convenience.
Yeah.
But it doesn't mean anything. But in as much as it's necessary in the time dimension and does mean something, one might worry whether these periodic boundary conditions, which we just impose as a convenience, whether they make any difference. And it might be useful, at least as an exercise, to switch to anti-periodic in the spatial directions and see if things change slightly or dramatically. If they just change negligibly, then everything's okay. If they change significantly, then people have to start worrying.
So I have one other kind of silly question. So you were talking about, this integral.
Wait a minute, I have to pay you for the
Okay,
question.
sure. Yeah, you were saying.
Is anybody starving here?
So you were saying, this integral is easy to do whenever it's Gaussian.
Excuse me?
You're saying
you
this
can
integral is
do
easy
the thing
to do
if it's
whenever it's
quadratic.
Gaussian.
Yeah.
If it's quadratic. I was wondering, is there anything that's analogous to a gamma function in terms of path integrals?
That's a good question because, in fact, the Gaussian integral is a special case of the gamma function, I think. And one thing I noticed was that certain other integrals could be done exactly in terms of the of the gamma function. But what screws you up is something that screws you up, you see. What you've got are also derivative terms.
Sure.
So in other words,
all you have to do is calculate the Green's function then for the.
huh? I mean, you've got derivative terms here.
Yeah.
So it's not as simple as a Gaussian where you just have one, or a gamma function where you just integrate over one variable.
Okay.
Here you're integrating over infinitely many variables, and they occur subtracted from each other in the exponential.
Yeah.
But it's worth pursuing. I mean, thinking about the gamma function. All right, let me tell you what the trick is for approximating ratios of integrals like this. And this is something that Glauber told me was invented by Fermi at Los Alamos during the war, the Second World War. And Fermi was using it Fermi did experiments as well as theory. And he mentioned it to Metropolis, who developed it. And then it turns out that the thing was finally published by Metropolis and his wife, and by the guy who is famous for the H-bomb. Anyway, he and his wife, so it's a 4-person paper that was published on this after the Second World War, when finally it was declassified. And the basic idea is that what we've got at any lattice point is we have some variable. Let me just call it x sub I. I'll label the lattice point by I, and x is the variable there. If we have one scalar field, then this would be phi at I, J, K, L, where I, J, K, and L are integers that label the point in this, the vertex of the four-dimensional lattice. And I would call this x sub I, where I corresponds to I, J, K, L. So just for notational simplicity, I'm just calling phi of I, J, K, L x sub I. And the first thing that we do is we let xi prime equal to xi plus some random number minus a half times delta x. This is a scale factor, and you choose it basically arbitrarily. R is a pseudo-random number. Pseudo-random number on 0, 1. And so you subtract a half from R so that you don't bias which way the x's go. And so this is the new value of the field at this lattice point, say. And what you're trying to do here, you see, is you have a probability distribution. The probability distribution of the field is e to the minus s of the field divided by the path integral over all fields, which is just this denominator. So the probability distribution is this, and what you want to get as A is you want to average A over a set of particular values of the field, and you want those values of the field to be distributed among all possible values of the field according to this probability distribution. And so basically what you're saying is that the mean value of A will be the sum of these AIs divided by 1 over n, as long as these AIs come from this probability distribution. And this metropolis step is what guarantees this. So let's say that S prime of xi prime, and when I say S, what I'm imagining is that S depends upon the entire lattice of values of xi, but now xi prime is the value, when you change the value of xi from xi to xi prime, then what we have is S prime of, and I'll just call that S prime. And so the probability distribution, the trick is this: you accept the new change with a probability x to x prime of e to the minus s prime minus s, well, let us say times beta. And to do that is you generate another random number, and if that random number is less than e to the minus s prime minus s minus beta, then you accept. So that means you accept, your probability of acceptance is exactly that, because you pick a random number, and that's the case. Okay. Oh, I'm sorry, I left something out. You accept under two conditions. You accept the change if s prime is less than s, and if s prime is actually greater than s, then you accept with this probability, which is to say you throw another second random number, and if this is the case, you accept. Let me maybe write this as an if-then-else statement. I'll write it in Fortran, but you can change it into C or whatever else, C or Java or whatever you use. So you've got to get a random number. Well, I'm sorry, I started writing too low. So the rest of the statement is you call a random number, and then you say if r less than or equal to, I'm sorry, if s prime less than, then you do this. Else you call a random number, and if r is less than or equal to exp minus s prime minus s times beta, then you also accept x of I equals x of I plus dx. And then you do end if for this if, and then another end if. So this is the Metropolis step in Fortran, and you can translate it into Java or whatever language you like to use. The next thing, so this is at a particular point in the lattice. The next thing you do is you go to the next point in the lattice and you do the same thing. That is to say, you make first a random change in the value of the field at that point. Once you've made that change, you compute what the change in the Euclidean action is for the field configuration, and this typically is just nearest neighbors. So you only have to check nearest neighbors. And if it's less than, if the change means that the action is less, you accept it. And if not, you have to throw another random number. And
wait, what if your random number is larger than exponential?
The random number generator gives you random numbers between 0 and 1.
Yeah, so what if it's larger than exp or minus beta?
Then reject.
Reject.
Oh, and you just make no change.
Right. So in other words, what's happened here, you see, is if the action's lowered, you change the value of x. Otherwise, you throw another random number. If and you accept with this conditional probability, but if both of those if statements are false or are not satisfied, then nothing happens to x because you haven't done anything.
Okay.
You
just like move to the next point in the lattice?
You just go to the next point, and you
Okay.
do the same thing.
Okay.
And you go on and on and on. And so then so now in practice, what you do is you go through the lattice. You start, first of all, with either all values of the field equal to 0, or all values of the field random at some scale, and that's said to be a cold start or a hot start. And then what you do is you go through the lattice and just run the metropolis step at every vertex over and over again until you sweep through the whole lattice, and you sweep through the lattice 1,000 times or 1,000,000 times, depending on how fast your computer is and how big your lattice is and how complicated the situation, the action is. And when you've done that a zillion times, then you can say that your then your lattice is thermalized, and it is producing field configurations that are distributed according to this distribution at the temperature beta that's given by the number of steps in the time direction. This is described in the path integral part of this is described in the chapter on path integrals in my book, and I'll try to remember to put that online if it's not already online. So basically, after it's thermalized, though, then what you do is every sweep through the lattice, you measure your observable, or every 10 sweeps, or every 100 sweeps, or every 1,000 sweeps through the lattice, you measure this observable, and then you just average it. And that's how you compute the mean value of a certain operator at a given temperature in a theory with a given Euclidean action. Now, the thing that I haven't quite explained is why this works, and that is to say, why this metropolis step leads to the right answer. And so let me try to do that. So consider two configurations, x and x prime, with Euclidean action s of x, s of x prime. And suppose they're occupied with probabilities p sub t of x and p of t prime, no, p sub t of x prime as the system is thermalizing. Now, let's suppose that s is greater than s prime. In my notes here, I was using energy instead of Euclidean action. And of course, energy is qualitatively the same. So, if s is greater than s prime, then the rate, r, to go from x to x prime, is first of all the rate v. V is the rate of choosing to test x prime, and which is to say it's v times the probability of being at x prime. So in other words, the rate at which you would change, in fact maybe I should put an I on this. the rate at which you would change the value xi to xi prime is the probability that xi would have the value, I should say xi prime, shouldn't I? Let's just make sure I've got this. Oh, I'm sorry, I was going x to x prime. So it's the probability that xi has the value xi times the rate of choosing to evaluate, to test that value at that lattice site. The reverse rate is the rate x prime to x. And this is the same v because the idea is that you go through the lattice and you choose, you do things symmetrically, you choose, you get to each site of the lattice an equal number of times, and then when you get to a site of the lattice, you go symmetrically up or down in a symmetric way. That is to say, you have a uniform random number, uniform on 0 to 1, subtract a half, and so that gives you an equal probability of going up or down. So the v's are the same. And the reverse rate then is the probability that you would be at x prime, but now it's e to the minus s prime times beta. And so here what I've been assuming is that s is greater than s prime. So if s is greater than s prime, then the rate to go from basically s to s prime is, you always accept if s prime is less than s. And so the rate of going from x to x prime is just the chance of being there and the chance of it being at x. On the other hand, the rate to go back is the chance of choosing, probability of being at x prime or x prime sub I. But now, you don't choose to go backwards with probability 1, you choose to go backwards with this probability, e to the minus beta s minus s prime, because s is greater than s prime, that's less than 1. And so, what happens then is that the probability p sub t of, let us say, xi over p sub t of xi prime, this is positive if and only, or the flow of probability from x, well, that's curious. All right, let's do the next, I've skipped the line here. The net flow of probability. That would be r of x to x prime, let me leave out the i's, minus the rate from x prime to x. This is this rate of choosing, but then it's the probability of being at x minus the probability of being at x prime, but the probability, so this is going backwards, and this has this other number here, so this has e to the minus s prime times beta. Maybe I should put a square bracket. Okay, this flow of probability is positive if and only if this structure is positive, and that's positive if p of x minus p of x prime is greater than e to the minus s prime times beta. And so the flow is toward x prime Well, I think the easiest way to see this is that the flow stops when these two guys are, when this thing is 0. That's the easy way to see it. And so the flow stops when p sub t of x, I, or let's just say x, is equal to p sub t of x prime times e to the minus s minus s prime times beta. But what this means then is that pt of x, well, is equal to e to the minus beta s of x times a constant, because you can just ignore the other stuff that depends upon x prime, because it doesn't depend upon x. So it stops when this is times some constant. So in other words, the flow stops when the probability of x at time t is proportional to e to the minus beta s of x. But that's exactly the probability distribution that you want, e to the minus s. Yes?
So this substitution t, this sub-index t, does that kind of means how long this...
How long you are in the simulation.
So is it possible to write the expression of how this flow goes in terms of a differential equation? So,
I've never thought of it that way. You could probably write it surely as a difference equation, because it is a discrete thing. That might be interesting. I mean, think about it. So, and then answer your question. So let me give you a candy though for that. In fact, it's, I think, so interesting a question that it's worth a candy. Okay, so this is basically, this is the demonstration of why the metropolis step works. There are generalizations and tweaks that you can make of the metropolis step, but and they're useful, but you don't need to tweak it. Now, here's one of the things that I really like about this way of doing calculations. It is remarkably robust. It basically always works. The disadvantage that it has is that it sometimes takes a long time to give you a good answer. But it always, if you give it enough time, it'll always get you a good answer. Now, there is just one thing about it that's tricky. The metropolis step and the logic behind it is not the first thing that most people would think of when thinking about this problem. In other words, how would you approximate that? Well, Fermi figured this out, but it's not immediately obvious that this is the right way to do it. It is the right way, but it seems to me that it's not manifestly obvious. And so for that reason, if you're writing a program to implement this on a computer, you can make a mistake because your intuition isn't much of a guide. At least mine isn't. And if you make a subtle mistake in the metropolis method, you get answers that are wrong, and they're robustly wrong. So you just have to, one of the things is you can't prejudice things in any particular direction. So you have to have r minus a half. You have to make sure that you evaluate that this v is the same for all points in the lattice. You don't introduce any bias. That's what you have to make sure. And then another thing is that if you're generating random numbers, you have to make sure that you initialize the random number generator correctly each time you run the program. You don't want to run the program 10 times to get greater precision, but use the same sequence of random numbers all 10 times. There was a group that did that actually, and they used, this was years ago, and they used up an enormous amount of computer time, but they had been rerunning the same random numbers over and over and over again. And I guess what they noticed is that the fluctuations were very, very small, and in fact 0, and so they caught on eventually. Okay, let me all right, let me say that there is a lattice site that's quite remarkable, and it's the lattice site of a quite remarkable physicist named Michael Kreutz. He's actually from New Mexico. His father worked at Los Alamos, and Kreutz was at Brookhaven National Laboratory on Long Island, and shortly after, I think it was after, but anyway, about the same time that Wilson suggested doing numerical calculations to evaluate path integrals to understand quark confinement and to understand quantum chromodynamics at strong coupling, where perturbation theory wouldn't work. Kreutz suggested using the metropolis method in the way I described on this in the last half hour. And in particular, he set up a website that has all sorts of very nice stuff. And this is the URL of the lattice site. It's lattice.net/lattice.html. I suppose this .html is superfluous, isn't it?
I think so.
Yeah, so let me just check that, because I don't want to have that there. So what he's got there are a variety of programs written in C, which you can download and run, and you can modify them. He's put in comments so that you know what many of the steps are in the what many of the steps in the programs do. His programs, even though they're some of them at least are treating simple things, are simple. You know, with C you can do very complicated things in very few strokes, and C code is hard to read. It's harder to read than Fortran. Harder to write also, I would say. Anyway, what you could do is download his code for Z2. So let me describe, I've described in general lattice field theory. In the lattice field theory, by the way, of course you've got a derivative, right? D by d x of phi. Well, on the lattice, you say that your lattice spacing is A, and you have this as phi of x plus A minus phi of x. So that's your derivative. And you have squares of these that occur all over the, and but of course this is on a lattice, so you don't have 5x. What you actually have is, all right, let me write this. All right, here, I'll write this just like that, but now what we really have is the derivative with respect to, let us say, xi, and this is 1 over a, and this would be, suppose this is, I'll say, suppose this is x2, then this would be I j plus 1 k l minus phi of I j k l. So that would be the derivative in the two direction, and it depends on which one is time. So you have to decide, is time your first one or your last one? So this is the second one in this case for the derivative. So that's your derivative. The action, if you're dealing just with the scalar field, is the square of that derivative summed over the different directions, all 4 directions. What is called lattice gauge theory is to take a gauge theory, but instead of just making this change, there also is another change that's made. And in particular, what you do is you put on each link of a lattice, you put a group element, let us say G. And if the group G is just, let us say, Z2, then what you're doing is you're just putting plus or minus 1 on that link. And your action, I see, I didn't write down the formula for what the action was. Ah, yes I did. Okay, the idea then is to, now this is Wilson's idealization or compactification of a gauge theory. See, in the real gauge theory, the gauge field A of x lies in, each component of the gauge field lies on the real line somewhere. In the compactification, well, in the case of Z2, I've never thought of Z2 as an ordinary gauge theory. So let's think of a group more generally. G can be U1, or G can be SU2 or SU3 and so forth. For quantum chromodynamics, it's SU3, of course. And so what you do is you put a group element on, so G1, G2, G3, G4, and now the action here would be the action of that. This is called a little square, and they use the French word paquet. I guess it's better to have one word than 2 words. Anyway, this is 1 minus the product of these group elements, or it's actually the trace of the product of the group elements. But this is the way the group elements go. G1, G2, because you're going around it, but now it's G3 inverse, G4 inverse, because you're going backwards. So this is and there may be a scale factor here, so 1 over n. The value of n would be, suppose all of these guys were the identity. So if these were n by n matrices, you divide by n. Okay, so so that's the action for a lattice gauge theory. In any event, there are really cute things that you can do with some of Kreutz's programs. I'll put this chapter on the class webpage and include it, and I'll talk about it next week. I encourage you to look at the exercises at the end. In fact, we might even just make these homework. There are 5 exercises. One of them is one of my exercises. It has nothing to do with Kreutz. The other 4 are, all right, let me just put it this way. Let's say, do one of the exercises. You can pick whichever one you want to do. All right, I guess we can stop, unless there's a question. All right.